Hello. Yeah. Good afternoon, everyone, and welcome to the day six, the final day of the student webinar lecture series by emerging researchers. We're glad to have all of you with us as we are closing out this 6-day lecture series, which has been designed to create meaningful learning experiences through student led sessions and expert insights from international institutions such as UCCR and UPR. Over the past few days, this webinar has brought together emerging researchers, mentors, and global faculty to explore key academic themes, helping participants build strong conceptual understanding while gaining exposure to real world applications and evolving research trends. As part of our life science career and research program, this initiative has aimed to strengthen the academic foundations and scientific perspective, also to connect with broader research community. Today we bring that journey to an end with two teams that tie together. The first one is the interdisciplinary AI solutions for complex scientific and technological challenges, where we'll explore how artificial intelligence can address complex problems through cross disciplinary approaches, combining insights from science, engineering, and technology. This will be followed by our concluding theme, which is the artificial intelligence for sustainable innovation in health, environment, and technology, where we'll examine how AI driven innovations can support sustainable progress across healthcare, environmental science, and the technology sector. Before we begin today's session, it is once again our privilege to acknowledge and welcome Dr. Sukant Kurana, whose work at the intersection of artificial intelligence, neuroscience, and healthcare continues to inspire students and researchers alike. His vision of building global research ecosystem has been instrumental in guiding initiatives like this throughout the series. With that, let us begin the final day of our lecture series.
Teaching is an important part of growing up as a scientist, to be an impactful researcher, impactful communicator. I wish the youngsters presenting today to a wider audience than just their research colleagues all the best. Go ahead and have a great day. Thank you.
Yes, now let's welcome our first speaker for today, which is Mrs. K. Vijayalakshmi, who has a background of MTech from VLSI, who will be speaking about the AI evolution.
Good evening, everyone. I am Vijay Lakshmi. Today, I am going to present on the topic Evolution of Artificial Intelligence. Artificial intelligence or AI refers to the ability of machines to simulate human intelligence. In simple terms, AI enables computers and systems to learn, think, analyze, and make decisions similar to humans. This presentation mainly focuses on how AI has evolved from basic machine learning systems to advanced intelligent technologies used today. For example, earlier AI systems were only able to perform simple rule based tasks. But now modern AI can generate images, understand human language, drive cars, and even assist in medical diagnosis. What this means is that AI has become an important part of our daily lives, as well as industries like healthcare, education, engineering, and business. In this presentation, I will discuss the major stages in the evolution of AI, including machine learning, deep learning, generative AI, and agentic AI systems. Let us move to the introduction of artificial intelligence. Artificial intelligence is a branch of computer science that enables machines to perform tasks that normally require human intelligence. These tasks include learning, reasoning, problem solving, and decision making. In simple terms, AI helps machines think and respond intelligently based on data and experience. This slide highlights three important components of AI. The first is data and AI. AI systems require large amounts of data to learn patterns and improve performance. For example, recommendation systems in YouTube or Netflix analyze user data to suggest videos and movies. The second component is intelligent systems. These are systems that can process information, learn from experience, and make decisions automatically. For example, virtual assistants like Siri or Google Assistant can understand voice commands and provide responses. The third component is advanced algorithms. Algorithms are step by step instructions that help AI systems process data efficiently. Modern AI uses complex algorithms to recognize speech, detect objects, and even predict future outcomes. What this means is that AI combines data, algorithms, and intelligent systems to create technologies that can solve real world problems more efficiently. Why is this important? Because AI is improving productivity, reducing human effort, and supporting innovation in many industries such as healthcare, education, finance, and engineering. AI has developed through several important stages over the years. Each stage introduced more advanced capabilities and improved the performance of intelligent systems. The first stage is rule based AI. These systems followed fixed rules programmed by humans. They could not only perform predefined tasks and were not able to learn from experience. The next stage is machine learning. In this stage, systems started learning from data instead of depending only on rules. For example, spam filters in email applications learn to identify unwanted messages automatically. After that came deep learning. Deep learning uses neural networks inspired by the human brain. This allowed AI to process complex information such as speech, images, and videos more accurately. Then we moved into generative AI. Generative AI can create new content like text, images, music, and videos. For example, tools like ChatGPT and AI image generators can produce human like responses and creative content. The latest stage is agentic AI. These AI systems can make decisions, plan tasks, and act more independently with minimal human support. What this means is that AI has evolved from simple programmed machines into highly intelligent systems capable of learning, creating, and reasoning. Because each stage of AI evolution is expanding the possibilities of technology and transforming industries across the world. Deep learning is a technique that allows computers to learn from data and improve their performance without being explicitly programmed. In simple terms, instead of giving every instruction manually, we train the system using data so that it can recognize patterns and make predictions automatically. This slide shows different types of machine learning. The first is supervised learning. In this method, the system learns using labeled data. For example, an email spam detector is trained using examples of spam and non spam emails. The second is unsupervised learning. Here, the system analyzes unlabeled data and finds hidden patterns or relationships. For example, customer grouping in marketing applications. The third is reinforcement learning. In this approach, AI learns through trial and error by receiving rewards or penalties. For example, AI used in robotics and game playing systems. Now, coming to deep learning. Deep learning is an advanced form of machine learning that uses artificial neural networks inspired by the human brain. For example, deep learning is used in facial recognition, self driving cars, speech recognition, and medical image analysis. What this means is that machine learning helps systems learn from data, while deep learning enables AI to solve more complex and intelligent tasks. Because these technologies are the foundation behind many modern AI applications used in today's world. Generative AI refers to AI systems that can create new content such as text, images, audio, videos, and even computer code. In simple terms, instead of only analyzing information, these systems can generate completely new outputs based on the data they were trained on. For example, tools like ChatGPT can generate human like conversations, while AI image generators can create realistic images from text descriptions. It also highlights foundation models. Foundation models are large AI models trained on massive amounts of data. These models act as a base of performing multiple tasks such as language translation, content generation, summarization, and question answering. Examples include GPT models, Gemini, and other language models. And it is important that a single powerful AI model can new perform many different tasks without building separate systems for each application. Another important concept shown here is natural language processing or NLP. NLP allows AI systems to understand and respond to human language more naturally. For example, virtual assistants, chatbots, and translation systems all use NLP technologies. Because generative AI is transforming education, business, healthcare, research, and creative industries by improving automation, productivity, and innovation. So, generative AI and foundation models are shaping the next generation of intelligent systems. Intelligent systems are AI based systems that can analyze information, make decisions, and perform tasks automatically with minimal human involvement. In simple terms, these systems are designed to think, learn, and respond intelligently based on situations and data. For example, recommendation systems used in Netflix, Amazon, and YouTube analyze user behavior and suggest personalized content automatically. It also introduces agentic AI, which is one of the latest advancements in artificial intelligence. Agentic AI refers to AI systems that can independently plan actions, make decisions, and complete tasks step by step to achieve a goal. An AI assistant may schedule meetings, send reminders, collect information, and organize tasks without continuous human instructions. that AI is moving from simple automation toward more autonomous and adaptive systems. Another important area shown here is decision making and automation. Modern AI systems can process large amounts of information quickly and support accurate decision making in areas like healthcare, finance, transportation, and cybersecurity. AI can help doctors detect disease earlier by analyzing medical reports and scans. Because intelligent systems and agentic AI can improve efficiency, reduce human workload, and support smarter solutions for real world problems. Today, AI is being used in many industries to improve efficiency, accuracy, and decision making. One major application area is healthcare. AI helps doctors analyze medical images, detect disease early, and support accurate diagnosis. For example, AI systems can identify signs of cancer from scans more quickly and efficiently. Another important area is education. AI powered learning platforms provide personalized learning experiences based on student performance and learning speed. For example, online learning systems can recommend study materials and practice tests according to individual needs. AI is also widely used in finance and banking. It helps detect fraud, manage risk, and automate customer support through chatbots and virtual assistants. In transportation, AI supports self-driving cars, and smart traffic systems. These systems use sensors and machine learning to improve road safety and traffic management. Another fast growing area is business and customer service. Companies use AI for data analysis, recommendation systems, and automated support services. What this means is that AI is no longer limited to research laboratories. It has become an important part of our daily lives and modern industries. Because AI applications are improving productivity, saving time, reducing human errors, and creating smarter solutions for complex problems. So, AI is transforming the way people work, learn, communicate, and live. AI is developing very rapidly, and researchers are continuously working on creating more advanced, efficient, and intelligent systems. One important future trend is explainable AI. This focuses on making AI systems more transparent and understandable. Researchers want AI systems to explain how they make decisions instead of acting like a black box. For example, in healthcare, doctors need to understand why an AI system predicts a disease before trusting the result. Another major trend is human AI collaboration. Future AI systems are expected to work together with humans rather than completely replacing them. For example, AI assistants can help researchers, engineers, and teachers by analyzing data and supporting decision making. This slide also highlights AI in robotics and automation. Researchers are developing intelligent robots capable of performing complex tasks independently in industries, healthcare, and space exploration. Another exciting area is generative AI and autonomous systems. Future AI models may become more creative, adaptive, and capable of solving real world problems with minimal human guidance. that AI research is moving towards smarter, safer, and more human centered technologies. Because these advancements can improve healthcare, education, scientific research, transportation, and many other fields. So, the future of AI offers enormous opportunities for innovation, technological growth, and global problem solving. Though AI provides many advantages, it also creates several challenges that must be addressed carefully. One major issue is data privacy and security. AI systems require large amounts of data for training and decision making. If this data is not protected properly, it can lead to privacy risks and misuse of personal information. Many online platforms collect user data to improve service, but improper handling of this information may create security concerns. Another important challenge is bias. In AI systems, AI learns from existing data, and if the training data contains bias, the system may produce unfair or inaccurate results. Biased data can lead to biased AI decisions. It also highlights job displacements. As AI and automation continue growing, some repetitive jobs may be replaced by intelligent systems and robots. For example, automated machines in industries can perform tasks faster with less human involvement. Another challenge is lack of transparency. Sometimes AI systems make decisions that are difficult for humans to fully understand or explain. In this way, AI development must be responsible, transparent, and ethical. Why is this important? Because ethical AI helps ensure fairness, safety, trust, and responsible use of technology in society. So, while AI has great potential, balancing innovation with ethical responsibility is essential for the future. Finally, let us conclude the presentation on the evolution of artificial intelligence. Artificial intelligence has evolved from simple rule based systems to highly advanced technologies such as machine learning, deep learning, generative AI, and intelligent autonomous systems. Throughout this presentation, we discussed the major stages in the development of AI and how technologies are transforming different industries. For example, AI is now widely used in healthcare, education, finance, transportation, business, and scientific research. What this means is that AI has become an important part of modern life and is continuously shaping the future of technology and innovation. We also explored future research trends such as explainable AI, human AI collaboration, robotics, and advanced autonomous systems. At the same time, we discussed important ethical challenges including data privacy, bias, transparency, and responsible AI development. Because the future success of AI depends not only on technological advancement but also on ethical and responsible usage. In simple terms, AI is helping humans solve complex problems, improve efficiency, and create smarter solutions for the future. So, artificial intelligence will continue to open new opportunities in research, industry, healthcare, and global development. Thank you everyone for listening to my presentation. I hope this presentation gave you a clear understanding of the evolution, applications, future trends, and challenges of artificial intelligence. Good evening, everyone. I am Vijay Lakshmi. Today I am going to present our topic explainable and trustworthy multimodal AI. This topic focuses on how artificial intelligence can become more reliable, transparent, and useful in healthcare systems. In simple terms, multimodal AI means AI systems that can understand different types of information together, such as medical images, patient records, and lab reports. For example, doctors use many reports together before making decisions. Similarly, AI combines different data sources to provide better healthcare support. Another important idea is explainability. AI should clearly show why it made a certain prediction or decisions so doctors can understand and trust the system. What this means is that AI can support healthcare professionals while still keeping decisions transparent and reliable. Because in healthcare, accuracy and trust are very important for patient safety. In this presentation, we will discuss the benefits, challenges, and future opportunities of trustworthy AI in healthcare. Today, hospitals and healthcare systems are using AI to improve diagnosis, patient care, and medical research. AI helps doctors work faster and more accurately. For example, AI can quickly analyze X rays, CT scans, and MRI images to detect diseases such as cancer or heart problems at an early stage. Early detection can help doctor start treatment sooner and improve patient recovery. In simple terms, AI works like a smart assistant that supports healthcare professionals in making better decisions. Another important application is patient monitoring. AI systems can continuously track patient health conditions and immediately alert doctors if there is any danger or abnormal change. It also highlights how AI reduces human error and saves valuable time in hospitals. Doctors often handle large amounts of patient data, and AI helps organize and analyze this information efficiently. What this means is the healthcare becomes more personalized and effective for each patient instead of giving the same treatment to everyone. AI can help create treatments based on individual health conditions. Because better accuracy and faster decisions can improve patient safety and treatment success. Overall, AI is transforming healthcare into a smarter, faster, and more connected system that benefits both doctors and patients. Even though AI has many advantages, there are still several problems that need to be solved before it can be fully trusted in healthcare. One major challenge is the lack of transparency. Many AI systems work like a black box. They provide answers or predictions, but doctors may not understand how the system reached that conclusion. It is like getting the final answer in mathematics without seeing the steps used to solve it. Another challenge is data privacy and security. Hospitals store sensitive patient information, and protecting this data is extremely important. If the data is leaked or misused, patient privacy can be affected. This slide also discusses bias in AI systems. Sometimes AI models may give unfair results if they are trained using incomplete or unbalanced data. For example, if the AI learns mainly from the one group of patients, it may not perform equally well for people from different backgrounds. What this means is that healthcare AI systems must be trained carefully using high quality and diverse medical data. There is also the issue of reliability in healthcare. Even a small mistake can lead to innocent diagnosis or treatment decisions. Why is this important? Because patient safety should always be the top priority in medical applications. Overall, this slide shows that solving these challenges is necessary to make AI systems more safe, fair, explainable, and trustworthy. The first foundation is transparency. AI systems should clearly explain how they make decisions so that doctors can understand and verify the results. If an AI system predicts a disease, it should also show which symptoms or medical reports influence the prediction. In simple terms, transparency helps users understand the thinking process of the AI system. The second important foundation is fairness. AI systems should provide equal and unbiased results for all patients, regardless of age, gender, or background. Another key factor is privacy and security. Since healthcare data is highly sensitive, AI systems must protect patient information from unauthorized access or misuse. This slide also highlights accountability. This means AI systems should be monitored and evaluated carefully, and humans should remain responsible for final medical decisions. What this means is that AI should support doctors, not completely replace them. Human supervision is still very important in healthcare. Trustworthy AI increases confidence among doctors, patients, and healthcare organizations. When people trust the technology, it can be used more effectively in real medical environments. Multimodal AI means combining different types of medical data together to improve healthcare decisions. For example, a doctor may use medical images, patient history, blood test reports, and voice information together to understand a patient's condition. Similarly, multimodal AI analyzes all these data sources at the same time. Instead of looking at only one report, the AI studies multiple types of information together for better accuracy. It also shows how multimodal AI improves diagnosis and treatment planning by combining different data sources. The system can identify diseases more effectively and reduce mistakes. Another advantage is faster decision making. Hospitals generate huge amounts of medical data every day, and multimodal AI helps organize and analyze this information quickly. What this means is that doctors can receive better support while treating patients, especially in critical situations. It also highlights improved patient monitoring and personalized healthcare. AI can understand each patient's condition separately and suggest treatments based on individual needs. Every patient is different, and personalized healthcare can improve recovery and treatment success. Overall, multimodal is helping create smarter healthcare systems that are more accurate, efficient, and patient focused. Machine learning allows computers to learn patterns from medical data and make predictions without being directly programmed for every task. For example, if an AI system is trained using thousands of medical images, it can learn to identify diseases like cancer, diabetes, or heart problems. The AI learns from experience similar to human learn from practice. It also compares traditional machine learning with advanced deep learning models. Deep learning models are more powerful because they can process large and complex medical data more efficiently. For example, deep learning is especially useful in image recognition, speech analysis, and disease prediction. The graph in this slide shows that advanced deep learning models often achieve higher accuracy compared to traditional methods. Is that healthcare systems can provide more reliable predictions and support doctors in making better medical decisions. However, these models also require large amount of data and high computing power. Sometimes they can become more difficult to explain clearly. Why this is important? Because in healthcare, doctors need both high accuracy and clear explanations before trusting AI predictions. Machine learning and deep learning are powerful technologies that are improving modern healthcare systems and support advanced medical research. Explainability means helping humans understand how AI systems make decisions. This is very important in healthcare because doctors need clear reasons behind AI predictions. For example, if an AI system detects a disease from a medical scan, doctors should know which features or patterns influence the result. Explainability makes AI less confusing and more understandable. It also introduces different explainability techniques such as feature importance, visualization methods, and attention mechanisms. These techniques help show how the AI systems process information. Some methods highlight important areas in medical images, while others explain which patient data had the strongest impact on the prediction. What this means is that doctors can verify whether the AI decision is logical and medically accurate. Explainable AI also increases trust between healthcare professionals and AI systems. When users understand the reasoning process, they are more confident in using the technology. Another benefit is identifying errors or bias in AI models. If the explanation looks incorrect, developers can improve the system. Why is this important? Healthcare decisions directly affect human lives, and AI systems should always be transparent and trustworthy. Overall, explainability techniques help make healthcare AI safe, more reliable, and easier for humans to understand. This slide explains the concept of human AI collaborative clinical systems. This means humans and AI systems working together to improve healthcare services and patient treatment. AI is very good at analyzing large amounts of medical data quickly, while doctors have human experience, emotions, and clinical judgment. AI supports doctors, but human experts still make the final decisions. AI may detect possible diseases from scans or reports, but doctors carefully review the results before confirming the diagnosis. This slide also shows how collaboration between humans and AI can improve efficiency and reduce workload in hospitals. AI can handle repetitive tasks, allowing doctors to spend more time caring for patients. Another important advantage is better decision making. AI can provide data driven insights which doctors use their knowledge and experience to choose the best treatment. This is that combining human intelligence with artificial intelligence creates stronger and more reliable healthcare systems. The graph in this slide highlights the balance between AI support and human supervision in clinical environments. Because healthcare requires both advanced technology and human understanding. Patients often trust doctors not only for medical knowledge but also for emotional support and communication. Human AI collaboration creates a balanced healthcare system where technology improves efficiency while humans maintain control ethics and patient care. Artificial intelligence is developing rapidly, and researchers are working on new technologies to make healthcare systems more advanced, accurate, and trustworthy. One important future direction is improving explainable AI. Doctors and patients should clearly understand how AI systems make decisions. In simple terms, future AI should not work like a hidden black box. It should explain the complete reasoning process in an easy and transparent way. Another major area of research is personalized healthcare. AI systems in the future may provide treatment especially designed for each patient based on their medical history, lifestyle, and health conditions. Wearable devices like smartwatches can continuously monitor heart rate, sleep patterns, and body conditions and send real time health information to hospitals. This slide also highlights privacy and security research. Since healthcare data is very sensitive, researchers are developing methods to protect patient information while still allowing AI systems to learn effectively. What this means is that AI can become both intelligent and secure at the same time. Another future direction is multimodal AI, where systems combine medical images, reports, voice data, and sensor information together for more accurate diagnosis and prediction. Researchers are also focusing on reducing bias and improving fairness so AI systems work equally well for all patients. Because healthcare technology should always be ethical, safe, and beneficial for society. The future of healthcare AI research aims to create smarter, more transparent, patient centered, and trustworthy healthcare systems. This slide presents the conclusion of our presentation on explainable and trustworthy multimodal AI in healthcare. Throughout this presentation, we learn how artificial intelligence is transforming modern healthcare systems by improving diagnosis, patient monitoring, and medical decision making. We also discussed how multimodal AI combines different types of medical data such as images, reports, patient history, and sensor information to provide better healthcare support. In simple terms, AI helps doctors work faster, more accurately, and more efficiently while improving patient care. At the same time, we also understood the challenges of healthcare AI, including lack of transparency, privacy concerns, bias, and reliability issues. To solve these problems, explainable and trustworthy AI systems are becoming very important. These systems help doctors understand how AI makes decisions and increase confidence in using the technology. This presentation also highlighted the importance of human AI collaboration. AI can support healthcare professionals, but doctors should always remain involved in final medical decisions. That technology and human expertise should work together to create better healthcare systems. Healthcare directly affects human lives, and patients must feel safe, respected, and confident while using AI supported medical services. Overall, explainable and trustworthy model AI has the potential to create smarter, safer, more ethical, and patient centered healthcare systems in the future. Thank you.
Yes, thank you, Jayalakshmi, for such a detailed explanation on the impact of AI across industries. Next speaker, we have Shubh, who is currently pursuing his bachelor's from Tapa Institute of Technology from Punjab. He'll be explaining about the medical image, like AI imaging in medical, especially with how machines are able to see the diseases. Let's over to Shubh.
Can you see my screen?
Yes, now, yes.
Okay. Okay. So, am I audible clearly?
Yes, yeah.
Okay. So, welcome everybody. So, this is Shubh, a final year undergrad in Thapar Institute of Technology. So, in the last session, which I in theme 10, where I presented about AI and medical imaging, in which we looked at different CNNs, different modalities, and how the modalities were adapted. So, now we are zooming out a little bit on instead of like asking about can AI read a scan, now we're focusing on how AI can help us to become a more sustainable world in which in different domains such as healthcare, environment, and technology, etc., so on and so forth. Okay, so I'll be keeping it very crisp and very just to be very to talk about all the fields properly. I just want to keep it a brief note about the fact that we'll be moving across 4 to 5 minutes for every slide. Okay. So yeah, so as you can see, there are like four big numbers which is mentioned. So let us start with the 17. So that's the number of UN Sustainable Development Goals. So researchers at Oxford found out that the AI could meaningfully accelerate at least 10 of them from health to clean energy to zero hunger. So then there's a tension of the same report found out that AI could hinder five of these goals if deployed carelessly. So AI is neither a savior, not a villain. It's a tool that outcome like depends entirely on how we build and deploy it. So walking to the three pillars. So health sustainability, global healthcare systems account for 4.4% of global carbon emissions, more than aviation. So keeping in fact the shift from the reactive treatment to AI-driven prevention is not just about the saving lives; it's about the reducing the systemic cost of illness. Environmental sustainability. Um, environmental sustainability, which is it's a Okay, just a second. Just a second. I think there is some issue. Hello.
Yes, yeah.
So for the first time in history, we have tools that can process the planetary scale sensor data in real time to satellite images, acoustic sensors at right. Yeah, sorry. Okay, acoustic sensors, atmospheric instruments. AI can synthesize all of this into giving a fact that intelligence we never had before. Technological sustainability. So here's the uncomfortable one. So AI is itself like a very high computing. So um, it becomes like consumes enormous amount of energy. So that means green air that we try to build the most efficient models using the renewable energy, measuring carbon per accuracy point is itself a research frontier. Okay. So again, three numbers: 400 million people globally lack access to this basic healthcare. Second, 30% of the healthcare costs are preventable with early intervention. AI has already cut drug discovery times by 2x. So like it's like timeless by 2x, like a half basically. So yeah, so these numbers are not hypothetical. They're motivated by these numbers basically. So for looking at the left column, we have the dominant model in global health today is reactive. So wait until someone is sick, then treat them. Then that's expensive. It's often too late and it's unsustainable at the scale. So AI flips this. WHO scale disease surveillance system now flag outbreak patterns week before they would be caught by international reporting. Sepsis production model in ICUs after alert clinicians hours before a patient deteriorates, and early intervention is dramatically cheaper and more effective than the last stage ICU care. So the mental health NLP is like particularly very interesting because systems trained on clinical notes can flag depression risk from how doctors write about the patients before any formal diagnosis. Okay, moving on to the right side of the page. So this is where the sustained angle gets real, and the consider a very rural part of India where a doctor is like between one for like approximately 1,500 patients on an average. So AI advisory tools don't replace those doctors; they amplify the reach of ASHA workers and ANMs who are already on the ground. Quantization and model compression mean a diagnostic AI that can once need on a cloud server can now run on a Raspberry Pi, no internet, no hospital, no specialization needed. Okay. So the traditional drug discovery pipeline takes like 12 to 15 years and costs over like like approximately $1 billion. Looking at these bars, the target identification alone used to like take like 2 to 3 years approximately. So AI has compressed this into weeks and like some cases basically. So moving on, so AlphaFold 2, so it is arguably one of the most important scientific results of the last decade. The protein structure prediction was a 50-year-old unsolved grand challenge. DeepMind solved it. So how they have done it? So the entire database of 200 million protein structures, combining up together, um, is now publicly available for the drug designer that they can finally see for lock before the key. So basically, and then moving on. So BioNTech or MNRAII, so which they have used the ML to optimize mRNA sequences for their COVID-19 vaccine. The same pipeline is now being used for personalized cancer vaccine. This is the same technology, just aimed at different target. So next we have in silico medicines. So this is basically uh, medicines IPF drug, like a fully AI generated molecule to enter human clinical trials. That's like a landmark that they've created. Next is the pandemic surveillance Blue Dot, a Canadian AI company. So detected COVID-19 in Wuhan 9 days before the WHO issued its public alert using NLP on airline ticketing data and public health reports. So the key point over here is that the open problems here are fascinating. How do you validate AI generated molecules. Basically, what are the liability frameworks for the AI designed drugs that they fall? And these are the questions that need computer scientists and biologists and lawyers to answer about the interdisciplinary problems. Okay. So moving on, so environmental challenges. So used to be hard to study at scale because the planet is enormous and sensors are expensive. Satellites change that. So AI changed what we can do with the satellite data. Some six domains which we have here is so the climate modeling and so just a second. Okay, sorry, yeah. Okay, so moving on, we have GraphCast, which runs 10 days, forecast 1,000x better than physics models, affordable and crime protection for developing the nations. So moving on, the biodiversity. So a bird net is a CNN trained on audio. You can record a bird calls in a forest. It will identify 6,000 plus special species and real-time researchers are using this to monitor the ecosystem health across the India's biodiversity hotspots without leaving their desks. Okay. Next is the plantics, which is used for the precision agriculture. We'll also go deep into the in the next slide and also talk about the crop disease diagnosis from a phone photo, and 50 million farmers are being involved in this. So energy DeepMind's RL system on Google's center cooling energy by 40%. That's a real deployed result, not research paper in hand. Next, we have the ocean and water. So ocean water coming out the Google Flood Hub, a 7-day flood forecasting for 80 plus countries covers the Brahmaputra and the Ganges corridors in India. Okay, next we have the disaster response, so in which we have dual stem vision transformers on social media and satellite data coming up to be the rapid impact mapping sectors. Okay, so moving on to the GraphCast architecture, traditional weather forecasting, numerical weather prediction is a physics-based thing. You solve the Navier-Stokes equation on a grid, it works, but it requires supercomputer that costs hundreds of millions of dollars. Developing nations simply cannot run this. So GraphCast takes a completely different approach. Step one, they take input in 6 hours of the global atmospheric state, in which they take features like the temperature, wind speed, humidity, pressure, etc. at 37 vertical levels of the atmosphere. Step two. So what they do is the graph's Earth's surface is represented as an in causal mesh of 40,000 plus nodes. A graph is a neural network, so passes a messages between nodes and then essentially learning which atmospheric conditions influence each other. Third is the atmospheric rollout, so in which it predicts the 6 hours ahead, so then uses that prediction to as an input to predict the next 6 hours repeated for the 10 days later and so on and so forth. Next, moving on, it outputs a ensemble of predictions with the certain uncertainty estimate because a forecast without an confidence intervals is not actionable. Moving on. Okay, it runs on a single TPU in under 60 seconds open source. Okay, moving on to the right hand side of the satellite imagery. So, okay, so for the crop yield prediction, we start with Sentinel-2 satellite imagery, free 10-meter resolution, updated every 5 days globally. We compute vegetation indices with like NDVI to track the crop health over time. We fuse this with weather data era 5 reanalysis from Copernicus, which is also free and open. A transformer based model then is being used to predict the field level of 6 per 6 to 8 weeks per pre-harvest, and then MAE can go between regions of like 5% in regions. So the output goes to farmers' phone as a practical advisory to irrigate or to fertilize or to pesticides, whatever, so on and so forth. Okay. So for the most ML history, you train one model per task. You had a chest X-ray, you had a land classification, you had a crop disease model, or so on and so forth. But the foundation model changes. You pre-train on enormous diverse data sets, text, images, scientific data, so on and so forth, etc. Like it can be other types of images as well, and then learn general representations of the world. Then you fine tune for a specific task with a very little label data. Looking at these before or after comparison on the left. So on the left, the task specific to general, millions of labels to few short, and the training from scratch to fine tune in hours. So why this matters for sustainability? So for sustainability applications, it's like a transformative. A lab in India works on flood mapping, doesn't need to collect 10,000 label satellite images. Then they take NASA specific model, all repeated on years of satellite images, and then fine tune on for their geography or with the fine tune of the 100 images. So that's like the cost and the time specifically for building each specialized model from scratch with a major barrier to entry foundational model lower than the barrier enormously. Okay. Next we have the MedPalm 2. So again, a Google Media Medical LLM model. So what they do is they expert level performance on the medical licensing exam benchmark. The multimodal versions, MedPalm M handles X-ray, dermatology images, genomics images from the same model. Next is BioVIL or Check Zero. So it's basically a clip-style model trained on radiology report and image pairs. So it's a zero-shot chest X-ray diagnosis, no task-specific labels needed at all. Next is AlphaFold 2. It's like, again, technically not a foundational model in the foundation, in the data, but it exemplifies the same idea about the how the model generates across the 200 million protein structures. Next is the GraphCast. GraphCast is basically all discussed like basically a global weather forecast of 0.25 in less than 1 minute, outperform ECMWF on 90% of metrics. Prithvi, again, a geospatial model, which is a, as I'll discuss. SAM is a zero-shot prediction model, which is work on medical imaging, satellite, and versions have been released in many fields, which have been designed for natural images, but researchers have shown it generates surprisingly well for medical imaging and satellite scenes with the minimal adaptations. Okay, so now we'll do some case studies, which is like a part of this presentation. So the GraphCast, so basically the state the problem clearly. The most accurate weather forecasting in the world is done by ECMWF, the European Center for Medium Range Weather Forecast. So their model runs on a supercomputer that costs hundreds of millions of dollars, euros basically. So most countries in the world, including the most of the South Asian Africa, cannot run this. The consequence is like the people in the flood-prone regions of Bangladesh or Assam gets like less accurate, so less timely warnings than anyone in London. So like that's a issue that we can pick up. So GraphCast changes the equation in DeepMind's evaluation. It outperforms the model on 90% of 1380 meteorological verification targets, and it runs on a single TPU, something a mid-tier research institution can access to Google Cloud for tens of dollars per forecast. The Hurricane Lee example is a particularly striking. The graph was correctly predicted the landfall location 9 days in advance. So ECMF MWF got it right in like at 7 days. So 2 extra days of warning can mean the difference between a successful evacuation and a catastrophe. So for the researchers in room, I would like to bring this very like upfrontly and saying GraphPass is open source. The ERA 5 training data is publicly available. You could right now download the model weights and run a regional fine tuning for an Indian monsoon pattern. That's the legitimate contribution that we could make for. Okay. So next is again a MedPalm study. So MedPalm 2 is a Google's medical question answering LLM. It scores at physician level of USMLE and MedC QA, PubMed QA benchmarks, which are genuinely hard tests on medical knowledge. So the multi-model version MedPalm M accepts X-rays, dermatology images, genomics, clinical notes, etc. So this is the direction travel. One model can integrate the full clinical picture. And then this is critical because benchmark performance is not the same as the clinical safety. The gap between the passes medical exam and can be trusted in a real patient care setting is enormous. Issues of hallucination, liability, workflow, and coming forward of integration and a completely answer for researchers. The interesting are in making a model smarter. They are making it safe, auditable, deployable in the resource event settings. Moving on, Google Flood Hub is a different kind of AI system, not a foundation model though, but a hybrid physics model. So hybrid physics model, I must say hybrid physics ML model, sorry, for flood forecasting. It uses LSTM networks combined physical hydrology equation trained on stream wash data, digital elevation models, and satellite perception estimates. It covers 80% countries and roughly 460 million people with 7-day warnings. So crucially, it works well in data sparse regions, unlike the traditional hydrology model that need dense sensor networks. For India, it's Brahmaputra corridor. Parts of the Assam and Bihar flood zones are covered, publicly available at floodhubgoogle.com. I would encourage all of you to go back and see after the session. Okay. So moving on, I want to spend some more moment on AlphaFold matters or beyond the headline for 50 years, determining a protein's 3D structure required like months of crystallography work costing hundreds of thousands of dollars per protein. The structure tells you how drugs might bind to the protein. Is a starting point for all the rational drug designs. AlphaFold predicts the structure from sequence in minutes. So with accuracy matching experimental methods. The entire database is like 200 million structures, is free and open access. A sustainability angle. So thinking from that point of view, so for the neglected tropical disease, malaria, TB, sleeping sickness, no pharmaceutical company was investing because there was no profit motive. Alpha Food was given academic and non-profit researchers the structural biology that they were previously only available to the big pharma. Next, Plantix is phone app that diagnoses crop diseases from a photo. Take a picture of the sick leaf and get a diagnosis and treatment recommendation within seconds. The model is trained over 400 crop diseases, pests, and nutrition deficiencies. It works offline. It works on a basic Android phone as well. So 50 million farmers, 100 countries. This is what AI for sustainability looks like in practice, not a research paper though. So, but a tool that a farmer in Uttar Pradesh or Maharashtra is using today. So the research challenge is the model was trained mostly on images from well-lit, well-photographed specimens. Distribution shift across the model variety, geography, phone camera quality, and lighting condition is a real and important problem to solve here. Okay, so opening the paradox that AI be sustainable while driving sustainability? So no, I want to make you very uncomfortable in this because everything I've been shown you here has been good news and the full picture has been more complicated. Read the call out slide here. So in which we'll be talking about training GPT-3 emitted roughly around 550 tons of CO2. That's the equivalent of 5 transatlantic flights per training run. So it's like basically a GPT is not even a large model by today's standards. So the field is growing exponential. The model size are doubling every year. If we are building AI to fight climate change, but the AI itself is accelerating the climate change, then we have the problem in that particular thing. So moving on, the compute and the carbon cost, not just training. So inference at scale also has enormous energy cost. The research problem here are model installation, the sparse architectures, and the carbon aware compute scheduling. So the algorithm bias at scale. So model trained on weird data fails silently on global south users data. So what does that mean is I mentioned in theme 10 for medical imaging that the same problem exists in every sustainable application. A crop disease model trained mostly on Californian smart will perform poorly on rich paddies in Bangladesh. An AI-based health scheme tool trained on Western patient population will fail immediately on Indian patient demographic. This is like hypothesis, a documented failure. Moving on, data colonialism. So this is a very hard conversation to hear for everybody in this room. So what does that mean is environmental data from Amazon or from India reverse system is being used to train the commercial models that are being sold back to countries as paid software products. So there is no benefit sharing, there is no government, there is no accountability. This is structurally similar to extractive colonialism, just with data instead of resources. Next, moving on to the regulatory gaps. So the FDA's 510K framework, as mentioned in my last set of presentation, governs AI as a medical device, but only in US, India, CDSCO frameworks is still evolving. International, there is no binding agreement on what validation standards an AI health system must meet before deployment. Okay, so there are some responsible government frameworks which are quickly move through it. So the first is the regulatory landscape, in which we'll talk about FDA 510K in US CE, marking in the EU CDSCO in India, all require pre-market validation for AI as medical device. The EU AI Act goes further; it classifies high-risk AI and mandates transparency, testing, and human oversight. Clinical in the loop. So what does that mean is, so this is a design principle, not just a regulation. It's like any estimate affects the patient's care must have a human in the decision chain. Otherwise, automation bias recognition over trust AI commission is a documented and a serious risk. Moving on to the prospective monitoring. So models degrade silently in deployment, distribution shift, maybe population changes, equipment change, updates, continuous drift detection is a operational necessity. Next is equity by design. This means collecting diverse training data intention, not as an afterthought. It means running subgroup analysis by age, sex, geography, ethnicity before claiming a model is ready for deployment. Next, is green AI. Compute reporting is becoming standard. Sorry, modules, models. Cards now routinely include training carbon cost. The ML Commons benchmark suite is adding efficiency metrics alongside accuracy, transparency. So model car data sheet for dataset, known failure, more document. These are now new standards practices at responsible AI labs and increasingly required by journals and conferences. Okay. So I have put this slide specifically for the audience because India is not just the market for AI assessment tools, it's a important proving ground for them. So if an AI health system can work at Indian scale with 1.4 million people, 22 official languages, extreme wealth inequality, and a doctor shortage, it can work anywhere in the world. India has one doctor per approximately 1,500 patients. So one like 1,445 patients on an average. The WHO standard is like 1 per 1,000. So AI isn't going to replace doctors. We don't have enough. So, but AI advisory tools amplify what ASHA workers and ANMs can do. So AIMS and Apollo are already deploying AI trial model tools in real clinical like workflows. So Ayushman is creating a unified patient data infrastructure. If a researcher can get ethical access to this data, federated learning across ABHA, that means Ayushman Bharat Health Account, linked hospitals is one of the important impactful research anymore that anyone will work upon. Okay. Architect in the not talking about the sorry, agriculture section. So 58% of Indian workforce is in agriculture. 40% produce the lost post-harvest, much of it due to disease, pest damage, and better monitoring to prevent. ICAR is already piloting AI systems. So the PM Kisan is also a PM database, and the Kisan Service apps are the infrastructure that research can build upon. Next is the environment. So 14 out of 20 most populous cities are in India. Real-time air quality forecasting using ML on low-cost sensor networks is extremely tractable research problem for this group. So ISRO's Mostak satellite portal is free and public. ISRO is actively collaborating with academic researchers. If you want to work upon the environmental AI and you are in India, then you have the better data access than most researchers globally. Okay. Moving on, now we have the problems that I would like to most, hypothetical research direction that we can build upon and, the people can work upon in this room. So I have also made sure that the level of the research by mentioning MS and ED so that the people, according to their levels of education, can pick up these research directions. Okay, the first is the problem one is the federated learning for Indian hospital network. So this is like a PhD level thing where the core challenge is non-IID data. Each hospital has a different patient demographic, disease prevalence, and equipment. So a standard Fed average breakdown. So personalized federated learning approaches like FedProx or FedMarks are promising but are explored in Indian context. Next is problem two, where we're talking about the lightweight XAI framing. So in which we'll talk about this is like for finally for MS, or UG final year. So GradCam and SHAP work on the powerful hardware. The challenge is the producing meaningful explanation for health worker using a $50 phone. What does a good explanation look like when your user is not radiologist? Next, moving on is the seasonal crop yield prediction for small households using open satellite or weather data. Next is species identification from acoustic data in biodiversity and hotspots. Then we have efficient fine-tuning of geospatial foundation models under the data scarce conditions. Then we have the green AI benchmarking, complete normalized evaluation frameworks. Then we have the bias detection and mitigation in multilingual clinical NLP for Indian languages. Moving on to the last that we have is the air quality forecasting for tier 2 cities, low cost sensors and are cheap and increasingly available. So, but the challenge is the calibration drift, again, the spatial coverage and the fusion with the methodology dataset. So, entirely tractable undergraduate project with, real public health impact. Okay. So career path that we can focus on research scientists, clinical AI specialists, founders, startups, agriculture, ML tech, and then we can have ethics, etc. So Now moving on to the last set of slide that we have is basically the takeaway that we have. Move on to the entire presentation is AI's value in healthcare goes beyond diagnostics, and then we have the predictive, preventive, and equity focused application where what are the next decade of impact lies. So imaging was where AI could work, but what we have covered today is where AI will prove it where it can matter. Next is environmental AI, not a niche. So what does that mean? Is climate, food, and water are civilizational challenges. Graph cars, flood harm, planting, etc. These are not like research prototypes and deployed systems affecting hundreds of millions of people. Next is foundation models lower than the barrier, but raise the stakes for fairness and governance. The efficiency gain from not training the model from scratch is the responsibility that comes with deploying the model at scale is equally real. AI sustainability is two-sided. We need sustainable AI and AI for sustainability. So both the engine problems, and that is are researchers in this workroom now. Moving on, the important open problems are not in architecture; they are in deployment, equity, and then evaluation and trust. The models are impressive though, but making them work safely in the real world environments are very hard. Okay, so six, India is uniquely positioned, scale of need, density of talent, and access to public health data. So the proving ground for sustainable AI systems worldwide is right here. So with this, I want to leave one thought: the problems I've discussed today are not solved. They are not even close to what we have solved. So the people who will solve are them in this room. Thank you.
Yes, thank you, Shub. So next, once again, let's welcome Vijay Lakshmi to speak about the AI in neurological disorder prediction.
Good afternoon, everyone. I'm Vijay Lakshmi. Today I am going to give a presentation on explainable multimodal AI for early neurological disorder prediction. In simple terms, this topic explains how artificial intelligence can help doctors analyze brain signals and healthcare data together for early disease detection. For example, disorders like Alzheimer's or Parkinson's may show early changes in brain activity, which AI can identify quickly. What this means is AI can support doctors in making faster and more accurate decisions. The system is also explainable so the results can be understood clearly instead of being treated like a black box. Slide explains how artificial intelligence combines knowledge from different fields to solve complex real world problems. In simple terms, interdisciplinary AI means AI is not working alone. It works together with healthcare, neuroscience, and data science. For example, in healthcare, AI can analyze patient records, brain scans, and EEG signals to help doctors identify neurological disorders earlier. At the same time, neuroscience helps understand how the brain functions, while data science helps process and interpret large amounts of medical data. What this means is when these fields are combined, the AI system becomes more accurate, intelligent, and useful in medical applications. This slide mainly highlights three important areas. The first is AI in healthcare, where machine learning supports disease prediction and diagnosis. The second is AI in neuroscience, where AI studies brain activity and neurological patterns. And the third is ethical frameworks, which focuses on patient privacy, fairness, transparency, and trustworthy AI decisions. Why this is important because healthcare decisions are very sensitive. Doctors and patients must understand and trust the AI system before using it in real medical situations. So, interdisciplinary AI creates a bridge between technology and healthcare to improve patient care and medical research. The increasing challenges in diagnosing neurological disorders around the world. For example, millions of people are affected by conditions such as Alzheimer's, Parkinson's disease, epilepsy, and other brain related disorders. In simple terms, the major problem is that many neurological diseases are difficult to detect at an early stage. Symptoms often appear slowly, and in many cases, diagnosis happens only after the condition becomes serious. It highlights that the large percentage of patients experience delayed diagnosis or misdiagnosis. What this means is patients may not receive treatment at the right time, which can affect their health and quality of life. Another important point shown here is the shortage of advanced diagnostic support in many healthcare systems. Traditional methods can sometimes be time consuming, expensive, and dependent on expert specialists. Why is this important? Because early and accurate diagnosis can help doctors start treatment sooner, reduce risks, and improve patient outcomes. This challenge is one of the main reasons why researchers are exploring AI based healthcare solutions. AI can analyze medical data faster and identify hidden patterns that may support earlier detection of neurological disorders. So, this slide explains why smarter and more efficient diagnostic techniques are becoming increasingly important in modern healthcare. Importance of combining EEG signals with critical healthcare data for neurological disorder prediction. In this, EEG records the electrical activity of the brain. These brainwave patterns can provide useful information about brain function and possible abnormalities. For example, doctors can use EEG signals to identify unusual brain activity related to epilepsy, sleep disorders, or other neurological conditions. At the same time, clinical healthcare data includes information such as patient history, symptoms, medical reports, laboratory results, and treatment records. When both EEG data and clinical data are analyzed together, the AI system gets a more complete understanding of the patient's condition. What this means is the prediction process becomes more accurate and reliable compared to using only a single type of data. It also highlights the concept of multimodal learning. That means the AI model learns from multiple sources of information at the same time. Similar to how doctors consider different medical tests before making a diagnosis. Because combining different medical data sources can improve early prediction, reduce diagnostic errors, and support better healthcare decisions. So it shows how EEG and clinical healthcare data work together to strengthen AI based neurological disorder and prediction systems. This slide explains how different types of medical data are combined to improve neurological disorder prediction. In simple terms, instead of depending only one source of information, the AI system integrates multiple healthcare data sources together. For example, EEG brain signals contribute about 35%, which helps capture real time brain activity patterns. Clinical healthcare records contribute 28%, including patient history. Lab reports and medications. Cognitive assessments contribute 20%, helping measure memory and attention functions. Finally, imaging data like MRI and PET scans contribute 17%, providing structural and functional brain information. What this means is combining multiple sources gives a richer and more reliable understanding of the patient's condition. This approach is called multimodal data integration because the AI learns from different types of information at the same time. Because using multimodal medical data sources can improve prediction accuracy, reduce diagnostic errors, and support better healthcare decisions. So it highlights how integrated healthcare data strengthens AI-based neurological disorder analysis. It explains the different AI models and deep learning methods used for neurological disorder prediction. In simple terms, deep learning is a branch of artificial intelligence that helps computers learn patterns from large amounts of medical data automatically. For example, the graph in this slide compares the performance of different AI techniques based on factors like accuracy, sensitivity, and specificity. Some models perform better in identifying brain activity patterns from EEG signals, while others are more effective in analyzing healthcare records and imaging data. What this means is different AI techniques have different strengths, and selecting the right model is very important for reliable medical predictions. It also highlights how deep learning models can process complex medical information much faster than traditional methods. They can recognize hidden patterns in brain signals that may not easily visible to humans. Because higher accuracy and faster analysis can support doctors in making earlier and more confident diagnostic decisions. Overall, it shows how AI and deep learning techniques play a major role in improving neurological disorder prediction and healthcare intelligence. This focuses on how AI systems can make healthcare predictions in a transparent and understandable way. Explainable AI, also called XAI, helps doctors understand why the AI gives a particular prediction instead of only showing the final result. If the AI prediction is a neurological disorder, it can also show which factors influence the decision, such as EEG brain signals patterns, patient symptoms, or medical history. The chart in this slide highlight important qualities of explainable AI systems such as accuracy, transparency, reliability, and interdisciplinarity. It also compares different explainable AI techniques used in healthcare applications. What this means is doctors and healthcare professionals can trust the AI system because they are able to understand the reasoning behind the prediction. Another important point that explainability reduces the fear of AI being related like a black box. Instead, it creates collaboration between human expertise and intelligent technology. Because the healthcare decisions directly affect patient lives, so AI systems must be trustworthy, ethical, and easy to interpret. Overall, it explains how explainable AI improves confidence, transparency, and responsible use of AI in modern healthcare. Slide explains how AI based healthcare systems can create practical benefits and real world medical applications. The technologies we discussed earlier are not limited to research alone. They can be applied in hospitals, healthcare centers, and clinical decision support systems. For example, AI can help doctors detect neurological disorders earlier by analyzing EEG signals and patient healthcare data more efficiently. This can support faster diagnosis and timely treatment. The graph shows in this slide represents the improvement and impact of AI systems over time in healthcare applications. It highlights how AI technologies are becoming more accurate, reliable, and widely adapted. This slide also mentions important real world benefits such as improved patient care, faster medical analysis, and better healthcare decision making. AI can reduce the workload on healthcare professionals while also increasing diagnostic efficiency. Another major advantage is accessibility. AI powered systems may help provide advanced diagnostic support even in areas where medical specialists are limited. Because of early detection and efficient healthcare support can improve patient outcomes and reduce medical risks. Overall, this slide shows how explainable AI and multimodal healthcare systems can create meaningful impact in the future of modern medicine. The future possibilities and research directions in AI based neurological healthcare systems. Future research can focus on improving accuracy of AI models by using larger and more diverse healthcare datasets. This can help AI systems provide more reliable predictions for different patient groups. Another important opportunity is the integration of wearable diseases and real time monitoring systems. Smart devices may continuously collect brain activity and health data, allowing earlier detection of neurological disorders. Researchers are also working on making explainable AI more advanced and transparent. This can help doctors understand AI decisions more clearly and increase trust in healthcare applications. This slide also highlights opportunities in personalized medicines. AI systems may provide customized treatment recommendation based on each patient's medical condition and healthcare history. In the future, collaboration between AI experts, doctors, neuroscientists, and healthcare organizations will become more important for innovation and medical research. Because continuous research and technological improvement can lead to smarter healthcare systems, earlier diagnosis, and better patient care. Overall, it highlights that AI in healthcare still has huge potential for future development and research advancements. Overall importance of combining artificial intelligence and neuroscience for better healthcare solutions. The first point highlights AI and neuroscience together. These fields can improve how neurological disorders are detected and managed. AI systems can analyze complex medical data quickly, while neuroscience helps us understand brain behavior and disorders more effectively. The second section focuses on explainable multimodal AI by combining EEG signals, healthcare records, cognitive assessments, and imaging data. AI systems can provide more accurate and reliable predictions. At the same time, explainable AI helps doctors understand the reasoning behind the predictions, increasing trust and transparency in healthcare applications. The next point discusses the interdisciplinary future. Future healthcare innovation will depend on collaboration between AI researchers, doctors, neuroscientists, and healthcare organizations. This teamwork can help create smarter and more patient centered medical systems. The final section highlights real world deployment. Advanced technologies like privacy preserving systems and real time monitoring can help implement these AI solutions in hospitals and healthcare environments safely and effectively. Because early diagnosis, intelligent healthcare support, and transparent AI systems can improve patient care and medical outcomes. Overall, the presentation shows how explainable multimodal AI has the potential of to transform the future of neurological healthcare. Thank you, everyone.
Thank you, Vijayalakshmi. Now we'll be moving to a different lecture for myself. And just a moment. Yes. So we all heard about how AI can impact industries and how it is actually impacting industries across right now in terms of the building the solutions, our agents, and even in the growth and research and all of it. But there's one thing that I've observed working as an AI engineer for the past 2 years now, that there are many companies which are in the race of AI particularly, and there are the top few companies, and then there are the ones like medium level companies or even smaller companies that are going towards it, and even individuals and all of it. So what I would like to claim is this something called as the mirror problem. What happens and what is exactly happening in the industry, which is the post research phase, right? Once we research something, implementation starts, and that's when problems arise and how we're going to target that. How AI can impact comes here if it's able to bring that impact across industries. And many industries are trying for solutions. Well, most of them fail after a few months of build development and all of that. So why it's happening is first we'll go through what the mirror problem actually is. Here we have seen in the past few days about OpenAI CEO mentioning even that the entry level jobs are not being taken at the moment right now, which was the claim earlier when AI was at the boom of beginning in the last year or so. And there have been contradicting statements across from all the podcasts you see or online you see people's fear of AI taking jobs and some people's fear of saying that AI will not take the job. Well, both of it is right. We have been seeing the trends in the industry right now where there are no mass layoffs according to the Yale Budget Lab found, as there is no significant change in unemployment for AI exposed jobs through March 2026. But also at the same time, there have been 115,000 tech layoffs in 2026 so far, and 50,000 cuts, explicitly citing AI, and Meta also cut off 8,000 people in this month alone. And companies are hiring fewer people for more output. So here, neither of them is wrong. It's just that the perception of what they're trying to say is different, and how we take it will be different. And what is happening here is neither. Because AI, what they're trying to say is AI as an individual system which acts kind of like a force of nature, but AI is not that. AI is something which is called as artificial intelligence. The full form itself says it, where if we talk about it, AI mirrors what you have taught it, right? Even the chat GPT or Gemini, it has been trained on bunch of millions of datas, and within the data only it's able to explain or answer to you based on that whatever it is learned. Just like if we go by humans, before we talk about AI, Let's talk about us. Like, think about it, right? You are shaped by everything around you: the culture you grew up in, the language you speak, the school you went to, the people you spend time with. A kid growing up around doctors sees the world through a different lens of health and diagnosis. A kid who grows up around engineers sees the world as systems and problems to solve. We don't form our thinking in a vacuum. We are mirrors of our surroundings. Now, in the right side here, you can see that AI is exactly the same. It's trained on data that humans created. It reflects our knowledge, our language, our biases, our blind spots. The model doesn't have opinions, it has a statistical reflection of what we fed it. And here's this thing that most people miss: even tomorrow, even when AI gets dramatically more capable, this does not change. It will still be shaped by its training data, by the objectives we set, by the guardrails we build. The surroundings change, but the mirror stays. And AI always takes the shortest path. What happens is you say, build me an auth system, and what you get? You get a login page and session management, security, token refresh. But what did you actually need? Do you need an entire authentication system or a simple one? So what AI does here is when you give a prompt, it takes the shortest path to achieve that particular task. It might skip a few things which it thinks is not necessary at the moment unless you specifically mention it in such a way. Here in the second one, we have just mentioning analyzes patient data. You'll get a summary dashboard, a pipeline that runs daily and alerts doctors. Or even when you say to help find you a job, you get a generic cover letter or a resume if you ask for it, and a target strategy and outreach system. So here the problem is it's not about prompting. Here, everyday software engineer jobs or even any other industries, the thinking is what matters. It's about how clearly you can think. And I want to be very direct about this is that the internet is full of prompt engineering courses, 10 magic prompts to make AI do anything. That's missing the point entirely. So here, vague thinking gives you vague output. Wrong framing gives you the wrong solution. But deep domain knowledge combined with a clear problem statement, that's when the mirror gives you something real. The prompt is just the last step. The thinking comes before that. That's what matters. And that's why an engineer who understands the domain will always get better results than someone who just learned clever prompt template. That happens with research too, because AI has been implemented in research, particularly in the recent years and recent time, where researchers are using it to get more sources or analyze a large number of data in a very short time. But the end of the time, it's what the researchers are thinking and how they are thinking, how clear they are in terms of what they're aiming for, that gives the better output for them. Here we have seen across, as I mentioned earlier, every company is going and getting the tag of AI. They want to get the tag of AI. Every industries, everywhere, the race of AI has already started. But many of them start something, and most of them don't survive until the production or until the users actually get some benefit from it. And why it is happening is because of these three gaps. So once these three gaps are covered, that's when AI evolution actually starts, where you'll see a lot of solutions that is used by a lot of people rather than only the people within the technology or within the industries. So what happens is let's talk about the first one. Here it is the most common one, and honestly, even I've fallen for it before. What happens is the timeline, right? You get an idea on one day, like let's say you get an idea on Friday, you wipe code an entire MVP on Saturday, and it looks good. It looks good in the initial. You show it to few people, and it works well. But you don't get any users because you can't scale it anymore, because the way it has been designed is how an AI coding agent will design it. It will it will take the shortest path to build something that works, that just barely works. And it works fine when you're the only one using it. It is not taught about all the software engineering principles that lays behind it. And that's what happens in everything within AI. If you are very clear about what you want, you can use it to amplify your work. But if you're not clear about anything, then you're not able to succeed in. The first thing when implementing AI across any industry is knowing what you exactly want from it in level from the source. And what happens there, once you know it, you're able to define it. And once you're able to define something, then comes the next stage where you can start building and working on it. And this is the second gap, that is the clarity gap. As I mentioned earlier, if you're very clear about what you need, so you can just mention, make me a calculator app, make me a fitness app, or an AI to do something, or why isn't it working? You see, if you give the very vague responses to the AI or very vague prompts, it works similarly. It finds whatever is closest to it because it is working on probability and stats. It gives you that itself. So the more clear you are, the more better you can use AI, and that is when, even across industries, the implementation will start working more once these gaps are covered properly and implemented in the right way. The next gap is the scaling. In, in scaling, the one thing is that kills the project that actually has a good idea. On the left is what most people think deployment looks like. You have a model, you connect it to users, done. On the right is what actually takes latency optimization, because nobody waits 8 seconds for response. You can build some things with offline LMs these days, but they take a lot of time to run on your local system because our laptops or our systems are not designed to run and compute at such a higher level that AI does, as are just CPUs, and even the newest one with GPUs are very low powered. So it won't work the way it should. And the users that you're targeting might not even have the devices which have such computation that your thing can run on, right? That is when this is where people fail in the scaling, because batching, even caching, because one user per GPU doesn't scale, and monitoring because models drift. We have seen GPT behaving weirdly, randomly at random times, or even been seen all the AI tools. Once moment it is working, the next moment is not working as expected. This is a very unglamorous work, right? This is engineering, and you need to be aware of it to be able to implement it across industries to be able to scale that. If idea is good, and then that implementation is something that users need, only then it will work. And the first thing that across industries that we have to think about before implementing any solution is it painful enough for the users to want to use it? Because at the end of the day, implementing AI, incurs a cost. It incurs a cost for the businesses, and businesses won't give things for free. So what happens is, you should be able to picture that in a way where, okay, if this is something that the users are able to pay for, only then that solution works. And also check about the alternate solutions. In industries, I see many companies doing that mistake of trying to build in a cool feature. A cool feature is not always a necessary feature, is what I would say. And that is being built right now and learned across many good project managers and companies where actual solutions are being built. And here in slide 13, I can give you my own example of it. And this is before and after from an inference optimization project I worked on. Same model, same accuracy, same answers. By applying proper engineering, the latency reduced by 93%. You can see the long red bar here, which is the native development, slow, expensive one, user blocking your whole GPU. That tiny teal square, that's after optimization. Same model, 93% less latency, less energy cost. This isn't research. This is what comes after the research. So for researchers as us who are trying to be a researcher, we should also think about, because at the end of the day, what we're trying to research is something that can contribute to the society in some or the other way, that should have a real impact. So thinking all of this will give a different perspective for us, even on the research end, is what I would believe in across industries that has been going around, and it will be implemented sooner or later in such a way where it will affect all the industries. And yes, many of the jobs might be taken away since everyone is running for the race of AI. But at the end of the day, the thinking is something that stays within us. So to be able to think and solve problems, or think in a way where you're very clear about what you know, and to be able to communicate what we know across industries, will help us also in terms of in our careers and also for everyone. And even in industries, that is the most optimal thing that industries look for, to be able to communicate what you think is the problem, the solution for it very clearly. And we connect this to the team of the day. Team of the day here, health, environment, and technology, because the pattern is identical in every industry, right? Healthcare, an AI system that reads X-rays between better than radiologist. The research paper exists. It's been published like multiple times, but we have to question, but does any hospital use it? Mostly, I don't see it right now at the moment because it doesn't fit into their workflow. The PACS systems doesn't integrate. The liability is unclear. The doctors weren't consulted, so it does. What works? An engineer who sits with a clinical team, understands their actual workflow, builds a tool that integrates into what they already do, not something that replaces them. And when we go to environment, let's say a team builds a gorgeous climate risk dashboard at a hackathon. It wins a prize and show it to a government agency. The agency says we don't use dashboards, we need automated alerts in our existing system. The dashboard dies. What works? A team that talks to the policymakers first, understand that they need a simple SMS alert when flood risk crosses a threshold, and builds exactly that. This is how industries are moving towards at this moment to build better solutions. And let's take an example of a technology, right? A company adds AI to their product. It's a chatbot that doesn't understand the industry, gives generic answers, and confuses customers. They announce AI powered on their website and hope it drives sales. But it doesn't work exactly as what they hope. But what works here is an engineer who scopes the real problem. Maybe it's search, maybe it's document processing, maybe uses RAG for domain specific content and actually measures whether the tool helps. The difference here is never the model, it's the operator. Every single time, it's the person behind building the systems that matters and changes the impact of AI across industries. So it's researchers and the engineers who do the work to get and impact the changes in the industries. And here, the job question that everyone wonders about, right? Let's come back to that. AI is not replacing any jobs, not but overall, not completely. But the thing is, it will replace tasks like maybe the email drafting, the data formatting, or the boilerplate code, right? Yes, those tasks are being observed, but the judgment, the decision making, the understanding of what to build, why, and that's not going anywhere. The people who will thrive, and this is what I genuinely believe, are the ones who will bring something to the mirror worth reflecting in the next evolution of AI. One is problem framing and the domain depth, and then engineering craft. The people ability to look at a messy situation and figure out what's actually worth solving. AI can't do this. It answers question. It doesn't know which questions to ask. And the domain depth, understanding the field well enough to catch when the model is wrong. If you don't know medicine, you can't tell when the AI hallucinated a drug interaction. If you don't know engineering, you can't tell when the code has a subtle rare race condition, right? And in the terms of engineering craft, turning a prototype into something that's reliable, fast, and cheap to run, the 93% deployment I showed you, that's not prompt engineering, that's system engineering. And it's the difference between a toy and a tool. And so, what do you actually do with all of this, right? Four things. One is start from the pain. Don't start from technology. Don't say, I want to use AI for something. Instead, find a problem that people are already spending money to solve badly or which has not been solved yet, which is being done physically through external ways, right? And that's your signal. That's the pain is real. To be a domain expert, AI is the tool, you are the judgment. The less you know about the field, the less useful the tool becomes. Invest in understanding the domain, not in learning prompt tricks. And the third one is think in systems, not in demos. A demo is step one of 50. Before you write the code or think about where does the data come from, what happens when the model is wrong, how much does it cost to run? That's what matters because everything comes down to how much it costs to run. We have seen bills or like news of Mercedes burning their AI monies, or even Microsoft banning cloud. We have seen all of those newses of how AI is burning money of companies of years worth of investment within months. So we should also first think about how much does it cost to run and who maintains it after it is done built. Fourth is like communicate like an engineer. Even though if you're a researcher, try to communicate like an engineer with clear inputs, clear outputs. Frame your problem so precisely that the shortest path is the right path. When you do that, when your thinking is so clear that AI's tendencies to take shortcuts actually works in your favor, that's when everything clicks. So, with this, I would like to leave with one idea. Just one is that AI is a mirror. Right now, today, it reflects the data that we trained it on, the problems we pointed at, and the clarity of the person operating it. Tomorrow, even when it gets more capable, that won't change. It will still be a mirror of its surroundings, just like we are. The question is not what will AI do to us, the question is what will we point it at? Point it at a clear direction and a problem with a clear thinking behind it, it will change the world. Thank you. Now, let's welcome Venkateshwaran TV with a background of MSc in biotechnology to speak about the applications of AI across industries.
Thank you very much, Ujjwal. There's something on here. Are you able to see my screen?
Yes, yeah.
Yeah. So, good afternoon, everyone. Well, looking at the title, you might be surprised as to why from galaxies to genomes. And taking a brief look at these words, galaxies or genomes, healthcare, scientific discovery, you might feel that these are separate entities where galaxies are studied through astronomical studies or genomes come under healthcare, like, and basically healthcare works on studies about various health disorders. Scientific discovery is a part of almost every science field. So, what is very common across all of them? So, in recent modern science, there is plethora of data, and also there is a very vast amount of data. And it's not the collection of data which is a challenge, but the main challenge is interpreting them and detecting signals and patterns and bringing them to a meaningful conclusion. That is what the challenge is these days. So that is where artificial intelligence is stepping in. They can see patterns. They can not only analyze the data, they can interpret it, they can see patterns, and they can even help you to find or finalize a meaningful result. So basically, what I want to say here is, so AI can work everywhere from the galaxy to human body or wherever, and we can talk about it in detail from here on. Yeah. So let's come to the evolution of scientific discovery. So when you walk down memory lane, how was science before artificial intelligence? How was science before any bioinformatics or computational tool? So what happened those days was the key to any scientific research or key to any scientific discovery was making or identifying a machine which can help a scientist observe things at a microscopic level, be it in biology or be it in cosmos. So, for example, telescope, you all know what a telescope is. Obviously, you will be able to visible stars, and you can see you will be able to see what is beyond this earth. And when you come to the biological application, which is a microscope, obviously these days we have a lot of microscope through which we can see through which we can see microbes like bacteria or even fungi or any other microbes. We can also visualize cells, and obviously there are microscopes where you can study especially the morphological structure of certain model organisms like Drosophila. And obviously, when the computer was invented, it started processing data. So let's cut to today. What do we have? What is the hot topic here? And that is artificial intelligence. So what is AI actually doing here? It's actually acting like a uh, modular intelligence. It's acting like a cognition itself. It gives you various information, and it gives you knowledge through different data sets, whatever field it may be. So in this slide, this is the major challenge, which is the data deluge, huge set of data. But this huge set of data is actually common across any field, be it the cosmos, which is space imagery, be it medical imaging, like it can be MRI, it can be a CT scan image, it can be a pathology image or a histopathology image. It can be even genomics or transcriptomics, which are applied in the medical field to study diseases. The main problem here is interpreting them. So, for example, when there is a James Webb telescope which can generate petabytes of space data, and so the interpretation becomes a challenge. And so, in all these cases, it is AI which is helping to speed up the process of the interpretation of data. It helps scientists to give a meaningful result out of all these data sets. And through this, you get the approximate or accurate knowledge of all these data. So next question is, why does AI work everywhere? So when I come to a very common example or a layman term, obviously we as humans will not be able to work in each and every sector because we are very specific. You come from school, and when you go into a college, you start specializing in a particular field, and you will in turn be narrowed down to a field, and you will only be working there. But that's not the case with AI. It can work across field. It can work across different domain. Because why? The only thing which AI identifies is that's it, nothing else. So it does not understand any galaxy or genomes or anything else for that matter. It's only data, and it understands different signals and patterns from the data, which obviously is present in every field of science. So now, uh, so astronomy was the field of science where people were compelled to integrate AI quickly. So when you see an image on the left, it's called a galaxy zoo. Well, it's not. It earlier it was not an AI based system. It usually it was dependent on civil scientists, and people used to analyze data and interpret it manually here, but it took a lot of time actually to come in to generate results. So what happened here is in recent days they have started integrating AI along with Galaxy Zoo, which helps in efficient data interpretation. So what it does, it can automate the morphology of the cosmic data, and it can also process the billions of objects, celestial objects from the telescope. Uh, and it also identifies rarer events from there. So basically, in uh, in a galaxy, you will have various celestial noises. So from there, it picks up certain patterns, and if there are any unseen anomalies, these the AI tools help in identifying them. So this is what we briefly discussed now. So one main aspect or one main application is the exoplanet detection. So as I said earlier, there is a stellar noise of cosmic data, and the need of the R is to identify a very subtle signal or any weak signal inside weak signal hidden in the cosmos. So that is where AI is really efficient. And so this finding a particular planet or a particular celestial signal is astoundingly similar to even finding a disease, because what happens when you are finding a disease or disease like cancer or any other disorder, in case of cancer, you look at a particular mass of cells from the plethora of cells inside the human body. So that is where these funda are similar. So both, so that is the meaning of this, because both require detecting a weak signal against a very noisy background or a highly noisy background. So the application ranges from planet detection to cancer detection. So what really happens here in the space science, like you have to detect a signal, then through that signal you have to see what kind of anomalies are there, and then you have to predict the outcome of those signal anomalies. So the similar thing is applied in cancer research as well. So you have to see a tissue mass where it looks like it would be cancerous, and then you should, and then what scientists do, if there is a particular mutation, they might flag it as a rare mutation, and they might say it is a pathogenic mutation and it could affect the physiology of a person. And so the next final process is what kind of outcome it can cause. So, for example, any lethal mutation can result in the death of the particular organism. So this is where this is the prediction part. So this is how the application of AI is very similar, be it from space science till tumor detection. So now, what kind of techniques did space researchers first develop to identify any different signals from the cosmos? So the first technique was denoising, where they remove the artifacts from all those faint signals. They analyze those properly and carefully, and they have to detect those signals. And they had to reconstruct the images, which means rebuilding very high resolution image from the data they have received. And the next process is feature extraction, where they have to identify a particular structure which is hidden. So all these is also applicable in medical research. And as the picture shows here, uh, this is a brain. It can be helped. AI systems can be very useful can identify anything, any abnormal signals, even if it's there in the brain or any part of the body. So the main take home from this slide is the techniques are shared, even though the field there they are applied in two different fields. E- Even though the fields here are different, you can apply them irrespective of the field, and you can identify the results. So now, as we have seen in earlier presentations, now in software there is a huge rise of AI, or we can term it a huge boom of AI. So now there is rise, not only in that, there is a rise of AI in healthcare as well. Name it radiology or pathology or ophthalmology or anywhere. Like scientists use AI to efficiently detect tumors or fractures or any lesions in the body, and they can even uh, identify the pathology, like by accelerating the grading of cancer, and even they can confirm the diagnosis through that. And even in ophthalmology, it can be used in identifying different diseases like diabetic retinopathy or even macular degeneration. So there is obviously a very high AI use in healthcare, and there are a lot of research lab which works on that. So application of AI in space, we have looked at the application of AI in healthcare. So now AI is application is also robust in identifying any defective genome in human body or even in any animal. So we can see we'll be seeing this later in the. I mean, like we'll be seeing it in detail in the later slide. So this is the outline. So there is DNA sequencing and AI analysis, and even and after that comes the clinical insight or the clinical result. So how is AI used in genomics? Well, this is used by a lot of companies, medical health-related companies, where who work on rare diseases like, for example, diabetes or any neurodevelopmental disorders, or even cancer, like le- irrespective of somatic or germline. So, what is when we talk about rare disease diagnosis? What's the main point here? In rare disease diagnosis, scientists look at any causal variant or any rare variant which might cause a disease, cause a particular phenotype in patients. So what happens in genomics is initially research labs used to analyze the genomics data manually, namely mainly Excel sheets, which was time taking. It needed very hard labor, and the results used to be very slow in those cases. So slowly, what happened is labs started using AI in order to prioritize variants. When I say prioritize variants, those variants are ranked according to their pathogenicity. Like the most pathogenic variants are ranked like top 5 or top 6, and the least pathogenic variants fall behind. So what does this automation do? See, this automation never completely replaces a human or a worker or a scientist. This aids scientists, like this fastens or speeds up the process of the analysis of genome, and it will keep help in giving more efficient results, more, and it can help in efficient clinical reporting, so that the patients can be able to understand, so that the patients will be able to understand them. And we also have polygenic risk score, which forecasts any susceptibility to disease even before symptoms appear. So now this is used in precision medicine. So what does this precision medicine mean? So before coming into that, so initially when we sorry, look into the medicinal aspect, or the uh, drug related aspect, or treatment related aspect in patients, it it worked on one size fits all kind of model. So what do I mean by that? So one size fits all means they used to give one particular drug for all the patients with those similar symptoms. But when you look into the microscopic level of it, that actually will not be the case. Why? Because each person will have a different genetic makeup. Each person will be encountering different environmental factors. Each person can be living a different lifestyle, and all those factors can play a major role in health of that particular person. So this is where personalized therapy comes in, and this personalized therapy is tailored for as per the molecular profile of every individual. So what does AI do? They integrate genomics, clinical, and the lifestyle data to tailor the treatment of that particular person. So this is how in the future it's going to work. And now comes a very interesting part, which is space medicine. So what happens exactly? Where is it applicable? So this is mainly applicable with astronauts. So they are space enthusiasts or space people who goes into space and studies various aspects of the cosmos. They collect information from there and all. So what's the difference here? You cannot have a direct doctor or a direct treatment if any astronomer experiences a particular discomfort in space. Obviously, one cannot travel that easily. So this is where AI comes in. And one interesting example is this crew medical officer who was assistant. Clinically, they have been able to identify muscle pains or even ankle injury and all, and the efficiency used to be was around 70 to 80%. So this AI tools can actually help in remote healthcare, and it can help in autonomous diagnosis, where it can look at the ultrasound image of the patient, and especially these AI tools like CMODA can work based on speech or text or any images. It can track patterns of the human physiology, and it can give them a particular diagnosis of what they are experiencing in space, and it can also give solutions to them as to what they can do temporarily to stop the inconvenience they face. And this could be very useful in in deep space missions like Mars missions. Now comes space biology. So this is basically there is this thing called microgravity. So all of you might have seen movies like Interstellar or any space videos or space documentary kind of videos where you will be seeing all those astronauts like floating in the air. So basically that is free fall. So during those free falls, what happens to them is they experience a sense of weakness there. It's actually not a complete loss of gravity, but yeah, the gravity is not there like the kind of gravity in space is not as much as in Earth, and it's very difficult for them sometimes to even settle down, and they actually feel some sort of weakness. So that particular weakness during the free fall is called a microgravity. So now these space becomes kind of tool to research on symptoms of aging. How is it possible? That's because astronauts symptoms like muscle loss or even bone density loss, and they can even their immune system might get dysregulated, and they might be also experiencing metabolic alterations. And all these symptoms which you can see here, they mirror diseases, they mirror phenomenon like aging. So this is how space biology and human physiology can be connected here. So that's why the space becomes a laboratory for human health by accelerating aging like process, which mirrors the diseases on Earth. So one of the major application is digital twin. So digital twin was initially an engineering concept. If you can see the image on the extreme left side here, you can see a twin of the spacecraft. So digital twin as said by people here earlier today, this is basically a virtual model of any system or any object or even any human. So here they simulate a space model here, and they can study how these spacecrafts work virtually. So uh, research is developing. So researchers are also applying this particular principle in order to study human physiology, just like how they have studied space using digital twin. So these digital twins of humans can obviously stimulate physiology, and they can be very useful in seeing what kind of treatments can be apt for a particular disease, uh, and it might even replace preclinical studies. So AI is also spreading its wing in drug discovery, and one of the main AI tool which studies the 3D structure of protein using the amino acid sequences nearby is AlphaFold, and AI actually, and with this AlphaFold, scientists can actually generate the hits for the targets. See, they can even identify different targets, and they can even look at the binding of drugs onto those targets, and they can interpret how those uh, drug interactions can actually help ameliorate the disease. So So basically, billions of molecules, drug molecules, can actually be can actually be screened. So, so if you see this figure, so this actually explains what we are seeing, and AI is the central hub here, and it is interconnecting all those research, be it robotics or even hospital or clinical research, laboratories or spacecraft. So this is basically one engine which is connected to many domains. So AI can be used to work on or work in all of these fields. So particularly the principle is similar. It's one principle, but it can do multiple tasks in various fields. So in future, AI can also be very useful in scientific discovery. They can they'll be able to generate hypotheses by looking into literature and framing a scientific question. They can even design experiments based on all the knowledge database of the techniques which are available. And obviously, they'll be able to analyze and even interpret various research. So this does not mean a complete replacement of scientists or individuals in labs. This means a more faster research. It could be more efficient research, and scientists will in future work with AI systems in order to study uh, various diseases or various pathways inside the human cells taking place, for example. So in short, it's going to be a collaboration between AI and researchers. So the next is foundation model, which is one model, many signs. So foundation model are basically artificial intelligence, neural networks, which works on various unlabeled data, and they usually trained on a particular set on vast amount of data, but they can work in different fields. Like for example, GPT, which is for language, and AlphaFold, which is mainly applicable for protein structure, and even for drug discovery, ESM for sequencing. So this shows that a single pre-trained model can actually serve various fields like astronomy, genomics, and even clinical medicine. So this is the entire picture of what we are talking about, the convergence. These might seem highly different fields to you, but the main common factor is big data everywhere, be it astronomy or even healthcare or any other field. And the main moderator is artificial intelligence, where they analyze, they look at pattern, they detect them, interpret all of those, and they can give you inputs according to those particular field. So now they are unified. So all these vast fields are unified by a single transformative technology. So the future vision, as we have said before, those are digital twins. It can be AI scientists, and you can give precision-based treatments to individuals. There could be collaborations between human and AI in the fields of scientific research, and of course autonomous discovery, which we just discussed in details some time back. So, what is the take home here? I would like to conclude with this. So, AI is one universal discovery engine. This this is being applied to various fields because they work on similar settings or similar principles. So these are the references where from where the slides were inspired from. So I am done with the presentation. Thank you.
Yes, thank you, Venkatesh. And with that, I would like to say that we'll be concluding the student lecture series for now, as this is the last day. Thank you everyone for joining, and for everyone who have made this a successful event for these many days. Thank you.